Now let's just quickly check if your grade 11 knowledge is up to scratch. Now there at the top, we have concentration, and tomorrow we're going to do all the mole calculations. So I'm not going to spend time on the mole calculations. We're going to do that tomorrow, right? But the next one is very important, and that is dilutions. How do you dilute something? By adding water, right? But now you have to be very careful. When you dilute an acid, do you do that by pouring the acid into water or by pouring water into the acid? You pour the acid into water. Now think about it. When you put acid and water together, it's exothermic, right? So it's giving off energy. So it's heating up. It might even make that some of that is spattered all over. So you will have, if you pour, you've got a big basin of acid and you put a little bit of water there in and it's heating up and it's splattering all over, what's going to splatter? You'll have acid splattering all over, right? Let's do it the other way. If you've got a big basin of water and you put the acid in there, it's heating up and it's splattering, what's splattering? Most of it is water, right? And if you remember from grade 11, water is very good with storing energy, right? It breaks a few hydrogen bonds and it uses a lot of energy for that. So if you've got water and you put the acid into the water, that water will be very good in absorbing the heat. And then you might even not have a splattering, okay? So you take the water and you put the acid into water, right? Not the other way around. And if you are diluting, you are actually taking a small bit of concentrated acid, and what do you add to that? What do you add to that concentrated acid? You're just adding water, right? You're just adding water. So if you look at this, the moles of acid in your original solution is going to be the same as the moles of acid in the final solution, because I didn't add moles of acid. I only add water, right? So the moles of acid is the same. I just added extra water. And then if you remember, C equals N over V, and therefore N equals C times V, and that's where that equation comes from. So you have to remember, the moment that they tell you they are adding water to dilute something, you have to use this equation. And it is not on your information sheet, right? It's not on your information sheet. Now, the guys who don't remember about dilution, what do? They take the titration equation. And even if you get the right answer, they give you 0 marks, because it's not a titration, it's a dilution. It is already 1-to-1, right? So whenever it's a dilution, you have to remember to put that. So if it's water they add, you will have, if you write the equation, ionization and dissociation. If you have to do a calculation, it is a dilution one, right? And the catch in this one is, you sometimes forget that the volume over there is not what you added. The volume over there is the total new volume, right? The new volume on this side is the original plus the water that you added. Right, to see if you understand that, turn the page and do 2.1 on page 24. 2.1, page 24. Can you see volume is on the left-hand side, but volume is always also on the right-hand side? So it doesn't matter if you're working in cube centimeters or cube decimeters, it will cancel out. Just make sure you don't put cube centimeters on one side and cube decimeters on the other side, then you'll have a problem. Right. So any unit, but the same one on the left and the right-hand side. So here I would have said how much water must be added to 30 cube centimeters of a 0.2 HCl solution. So I start with a 0.2 solution and I have 30 cube centimeters of that. And then they say, I want to change the concentration, so afterwards the concentration should be 0.03. And then I get the new volume, 200 cubed centimeters. And is that what they asked me? No, they did not ask what is the new volume, right? They ask me what must be added. So if I know what is added, then I will say I have to end up with 200, but there was already 30 in the container. So I only had to add 170 cubed centimeters. Right. So that is often one of the first questions when you get to titrations, for instance. They have you calculate a new concentration or asking how much water to add. Right. I would like you to go on with 2.2 next. They tell you a solution of acid HX with a concentration of 0.15 is prepared. So they have H, and they're telling you it's an acid. And they say the concentration of the hydronium ions in the solution is 3.2 times 10 to the 6. And now they ask you, write an equation for HX and water. So we start off, HX and water. HX, they told us it's an acid. So what type of reaction do I expect? Ionization, and I have to put the water in there. Right. And what will happen? Now, I don't know if it's weak or strong yet. I'm just going to say acid is a proton donor. So the proton will be donated, and you will end up with X, and there definitely must be a minus over there. And then this one will become H3O plus in solution. Right, so you have minus and plus, just check that one. Right, and now we get to the second part, and the second part is the more interesting part. They are asking, is this a strong acid? And the answer was? And the answer was no. Right. Okay, let's talk about this. What is your definition of a strong acid? Ionized completely. So if I made a solution and I put 0.15 into every cube decimeter, and it was a strong acid, how much of the H3O plus would I have expected? 0.15. And what do they tell you? They tell you there's not 0.15, there's only 3.2 times 10 to the minus 6. So only a few of those that you put in actually went over. So the answer is definitely no. And I will say that because the H3O plus concentration is so much smaller than the HX that I put in there, right? That shows me that it ionizes incompletely. It ionizes incompletely. And now they're asking us to name the conjugated pairs. Now, what do I have to remember? A pair only differ by H plus. So if I look at HX, who is paired with HX? HX and X minus, right? They are a pair. And who's paired with H2O? H2O and H3O plus is a pair. Right, everyone happy? Okay, so that was grade 11. If you turn back one page, you finished with grade 11. And I think we're ready now to move on to grade 12. So what we are going to look at is the O2 protolysis of water and also the pH scale. Now, let's think about water. Water, we call it an ampholyte or an amphoprotic substance. Tell me what's an amphoprotic substance? Yes, something that can either react as an acid or as a base. So let's take a reaction where one molecule acts as an acid and the other one acts as a base. So the acid is a proton donor and the base is a proton acceptor. So what will happen? We will end up, this one will become OH minus, and that one will become H3O plus in solution, in solution. And that's why it's called it O2, right? Because it's water with itself. Protolysis because it's transferring a proton, right? Electrolysis will be an electron this is protolysis, it's a proton that is donated. Right, so we have that one. Now, if I want to write the Kc expression for that one, what should the Kc expression for that one look like? It should be OH minus times H3O plus concentration divided by 1. Yeah, nothing, 1. Okay, right, because these are pure liquids. They don't even come in. So your Kc equation looks like that. Now tell me from Monday, what influences my Kc value? When will my Kc value change? Temperature. Right, temperature. Now, if you look at your page with information, that orange one, you will see there you have this, but they've now exchanged that small c for a W. Water is so important. You are actually 70% water, so it's very important. Huh? Water is so important, we're going to change that C to a W, and we call it Kw value. And if you look at, come on guys, over there. Right, attention. If you look at this one, it gives you Kw, there you've got your Kw equation, and where does it give you afterwards? It tells you that if you are at 298 Kelvin, which is the same as 25 degrees Celsius, because you subtract 273, do you remember? Right. So if you are at 25 degrees, then the Kc value is 1 times 10 to the minus 14. 1 times 10 to the minus 14. 1 times 10 to the minus 14. But that is only true when you're working at 25 degrees Celsius. And the reason why they chose 25 degrees Celsius is we want to work in the lab without always making things cold or making things hot, right? We are usually at more or less 25, so it's easier if we just learn one of them by heart. So this is the one they give you. If they want you to work at a different temperature, they have to give you a new Kw value, right? So we look at this, Kw, 1 times 10 to the minus 14. Now I want to ask you, is this a big or a small one? Is this big or small? This is very small. So if I take this water in this bottle and I was able to count which of these H2O molecules in there occur as molecules and which of them have split up into OH minus and H3O plus. How many of them will be H2O molecules and how many will have split up into ions? Nearly nothing is in the ionic form. Once you take the ions in there and you multiply it, you get 1 times 10 to the minus 14. So if you drink this water, there's more or less no ions in there, right? No H plus and OH minus due to the water if it's pure water. You only have H2O molecules more or less. Little bit. Once you've multiplied them, you get that very small 1 times 10 to the minus 14. Now if I have pure water, pure, how does the OH minus and the H3O plus concentration compare? Come on, it's pure water. No one else put OH minus or H3O plus in there. Then there will be 1 OH minus for every 1 H3O plus. Everyone happy? Okay. This means those two are exactly the same, and I can say that's H3O plus squared. Because they're both the same. I can just say it's squared. And then if I go and work this out, H3O plus, I will end up with 1 times 10 to the minus 7 moles per cube decimeter. So I can ask you, what is the concentration of H3O plus ions in pure water? It's little, hey? 1 times 10 to the minus 7, 0.000, stop me, 1. Right. So there's very little. Okay. So the first thing you have to remember is that Kw equation. We're going to use that whenever we are in solution and we want to go from OH minus to H plus or from H plus to OH minus. We're always going to do that with the Kw expression. Right. And then the last thing is pH. pH, if you remember, is negative the log of H3O+. Right. It's the potential of hydrogen. You get other things like PCl. It's the potential of chlorine. POH. So there's a lot of P things, but we're only doing pH. Is the potential of hydrogen ions in there. So it is negative the log of H3O+. And now, if I've got pure water, what do I know about H3O+ in pure water? In pure water, that is 1 times 10 to the minus 7. And if you work it out, you end up with 7. Right. So pure water's got a pH of 7. It was not chosen. It worked out that way. Right. Pure water has got a hydrogen concentration of 1 times 10 to the minus 7. Therefore, it's got a pH of 7. Right. Now, we're going to do a lot of calculations with things like this. But if you go into your summary, I will see on page 21. If you go to page 21, you will find this diagram over there. The diagram is supposed to help you. The diagram is supposed to show you how to get whatever you want. So if for instance tell you you've got an acid and they give you the concentration of the acid and they ask you the pH, you start by saying for pH I need the H3O+ concentration. Right. But that is not necessarily the same as my acid. If my acid is HCl, what do I know about HCl? It's a strong acid, right? And then if I write it down, how does HCl react? HCl, it's a strong acid. That tells you that it will, strong acid, it will ionize completely, right, completely. So if you look at what happens, if it ionizes, it will give Cl- and H3O+, and then you can say, aha, it ionized completely, and for every HCl that I start off, I end up with H3O+. One of these will make one of those, right? So if they told me I've got an HCl concentration of, say, 0.3 moles per cube decimeter, then now I can say, okay, so therefore, my H3O+ concentration is also 0.3 moles per cube decimeter. Because I know every single molecule is going to do that, right? Because it dissociates, ionizes completely, and I know it's only making one. So if you think about your strong acid, HCl, how many hydrogens is it going to produce? 1. HNO3, 1. And H2SO4, 2. So the only ones they're going to ask you the pH are your 3 strong acids. And if it's HCl, it will give you 1 H+. So their concentrations will be the same. If it's HNO3, then obviously it's also only giving 1, then their concentrations will be the same. But if it's H2SO4, then they're in the 1:2 ratio. Right. Okay. So just remember, concentration of acid is not necessarily the concentration of the H+. Sometimes you have to get it. And now, how about a base? If they give you a base, what do? Base, they can only give you a strong base. Strong base will give you OH. How do I go from OH to H+? Kw value. Right. How do I do that pH? Just put it into the equation. So it's not that difficult if you have the sort of the layout of the land, how you're working. Okay, let's see how you fare on that one. On page 24, once again, we're going to do 2.3. Can I quickly have a show of hands? Who's IAB? Okay, you don't do pH calculations. So just leave number C, just do up to number B. If something is wrong in the exam paper, you don't go falling apart because it's not your problem, right? You do your best with what they give you. You write there, I need the volume or whatever. Right. Or you say, I assume I am using volume this or whatever, and you go on. Right. Because if there's a problem in the exam paper, they will give you the marks. So don't go feeling all shattered, right? If something is wrong in the exam paper, oh wonderful, they're going to give me the marks. Continue with the rest. Okay. So in this instance, there was a typing error. There had to be 300 cube centimeters. So it was x cube centimeters of water is added to a 300 cube centimeters of a 0.15 mole per cube decimeter sulfuric solution. Yes. So there was no way to know that except if they gave it to you. Right. So if they gave it to you, you put it in there, and then you would have worked it out, and it would have been 1,000 cube centimeters. And then you said, okay, but what should I add? I have to end up with 1,000, but I already started with 300. That means I had to add 700 cube centimeters. Right, but that was just revision. Okay. I think I'm going to give you a few seconds now because you couldn't go on because you couldn't do the first one. Just go on and see if you can do B and C. I am asking for the hydronium ion concentration. They're giving me sulfuric acid. Now, whenever you change from substance, you're supposed to have a ratio somewhere. So the first thing I'm going to say is, what do I know about H2SO4? It is a strong acid, and therefore I can assume that it will ionize completely, right, completely. And how does it ionize? It will ionize by giving off 2. So I will end up with SO4 2- and 2 H3O+. And that shows that the H2SO4 to H3O+ ratio is 1 to 2. Right. So if the concentration of the solution, right, and we're working with the final solution, the concentration, I think you should add that final just not to make it to make it clear. If we're working with 1 to 2, then what will be the H3O+ in the final concentration is 2 times the 0,045, which is 0,09 moles, thank you, moles per cubed decimeter. Right, so that was the question. They asked me, okay, we now have this concentration. Yes, sure. Right, we started off with a 0.15, and we diluted it, and now we ended up with a 0.045. And now this is a sulfuric acid. So what we have is now we have the concentration of the sulfuric acid is 0,045. Is that what you wanted to ask? Right, because the important thing is the concentration of the acid is not always the concentration of the H+, right? So what do we know about the acid? We know it is strong. That means everything is going over. And then how is it going over? When it is reacting, it is producing 2 H3O+. So the H2SO4 to H3O+ is 1 to 2, and therefore, perfect. Thanks. Okay, so that is the second one, number B. And then the very last one is easy. They're asking pH, it's just putting it into the equation. And if you have negative the log of 0.09, then you end up with 1.05. Is that what you would have expected? What do we know about sulfuric acid? It's a very strong acid, and a concentration of 0.09 is actually still strong. Right? So you've got a lot of it, and all of it will give you H+, and each one will give you 2 H+. So you end up with a lot of H+. Right. Now, this was for an acid. Let's see if you can do the same thing for a base. So you can move on to 2.4. I will leave it here if there's someone who's writing. Move on to 2.4. Right, just quickly do number A together. Number A, they asked you if they have 0.5 grams of lithium hydroxide and it's used to prepare 200 cube centimeters of solution. And now they ask you calculate the concentration. Now, we're going to do a lot of mole things tomorrow, but you should have this one from grade 11. Right, to work out the concentration, small m is the mass that they gave me, 0.5. Big M is the molar mass. Where do I find that? Periodic table, right, periodic table. We're working with lithium hydroxide. So you just add together all the masses and you will get 24. Right, and then what's the catch? Volume. There's only one volume in this one, right? If there's only one volume, then that volume should be in cubed decimeters. So I take my cube centimeters and divide by 1,000. Then I end up with cube decimeters, right? And if you do that correctly, you end up with 0.10, actually 4. And that depends, if you're rounding off, you can leave it like this, or you can use the 4. It will make a little bit of difference in the funnel, but they mark both, right? So, do you want to leave it like this? Okay, nice, okay. Mole per cube decimeters. That was for A. Now we have the concentration of lithium hydroxide. So this is for lithium hydroxide, the concentration. And now in the second one, they ask us, what is the concentration of the hydroxide ions? Now, what do I know about lithium hydroxide? Strong base. You see why that first table is so very important, right? It's a strong base. And what do I know about a strong base? It dissociates completely. And just show me how it dissociates. Now, dissociate, should water go into the equation or not? Nope. So it will make a lithium plus and it will make OH minus. And you can put aqueous there if you want to. Right, so what does it show you? It shows you the lithium hydroxide to OH minus. One of these will produce one of those. And immediately I know, okay, so my OH minus will also be 0.10 moles per cube decimeter. Because every single one that I put in will make an OH. They react completely. Okay, and then just to make things more interesting, with C, I ask not the hydroxide, but the lithium ions. Well, I've already written the equation. If I produce one of those, I also produce one of those. So they've also got the ratio 1:1, so that answer will also be for the lithium ions. It will also be 0.10 moles per cube decimeter. Same thing. Right. Now we're up to number D, hydronium ion concentration. I've got OH and they're asking H3O+. How do I go from H3O+ to OH minus? KW. So it's a quick. Whenever you want to switch between H3O+ and OH minus, we're going to work with KW. Now, if they should actually tell you that they're working at 25 degrees Celsius. But if they don't tell you, just assume that you're working at 25 degrees Celsius, so that you can use KW is 1 times 10 to the minus 14. And I'm looking for H3O+, and the OH minus I already have, 0.10. And then you get your H3O+ concentration as 1 times 10 to the minus 13 moles per cube decimeter. Right. Now, if you haven't rounded off there at the top, if there at the top you left it as 0,104, then you would have ended up here with 9,62 times 10 to the minus 14. It looks a lot different, but it is actually not. Right. So it depends on your rounding. Right. If you round it off to 0.10, you will end up with 1 times 10 to the 3. And then pH is just putting it into the equation. Negative the log of the H3O plus, negative log of 1 times 10 to the minus 13 to give you a pH of 13. And if you haven't rounded, you would have ended up with 13,02. Is it getting better? Yeah, it's not that difficult. Whenever you have H plus and you're looking for OH minus, KW, right. Can you do anything with the pH other than get the H3O plus concentration? No. So if you come into a strange question and you have a pH, put it into the pH equation and get the concentration of the H plus. Let's look at the next one together. Now, sometimes you've got a few calculator problems. Going back. Now here they give you the pH. They don't give you the concentration and ask the pH. They give the pH. So we have to move back. pH, negative the log of the H3O plus concentration. And now they give you pH. They give you that side. Okay. Now, if I want the H3O plus, the very first thing is to take the negative over to the other side. So you get negative 11,61 is equal to log H3O plus. Right, so I took the negative over. Now I want to take away log here. If I take away log on this side, I have to add a 10 underneath there, because that is what log means. Right. What is the number if we have it to a ground of 10? Right. Now, how do I do this on my calculator? I will say second function log of minus 11,61. Second function log, right? You want the inverse of log, second function log of minus 11.61. And then you should get your H3O plus concentration as being 2.45 times 10 to the minus 12 moles per cube decimeter. Right. Is your calculators agreeing? Yes, it's not that difficult. Right. So remember, you're taking the negative over, because some people forget about the negative and then everything goes haywire. Right. So, but have we answered the question? Well, we've calculated H plus, but we haven't calculated OH minus. How do we get OH minus? KW, nice. Assuming we're at 25 degrees Celsius,